Hello everyone, welcome back. Myself Usha Mirejkar, Selection Grade Lecturer, Electronics and Communication Department, Government Polytechnic, welcome. Today we are going to study the subject Advanced Communication, that is for the 5th semester Diploma Electronics and Communication Engineering students. In this, the unit is the Unit 2, Radar Principles and Applications. This is the session 9. The contents which we are going to cover in this particular session are continuous wave radar disadvantages. As you know, in the already last session, we have studied about the continuous wave radar, which is making use of the Doppler shift here. The main purpose of the continuous wave radar is to find the relative velocity of the target. But one of the major drawback is what? It is unable to find the range there, distance. Therefore, here the disadvantages, we will review both those things once again here. Next is the frequency modulated continuous wave radar principles. Block diagram of frequency modulated continuous wave radar. Advantages. MTI principle. Block diagram of MTI. And about the blind speed. Now the disadvantages of the continuous wave radar are, that is, its transmitting power is limited, which reduces the maximum range here. It is easily confused by the presence of large number of targets. And one of the major drawback is what? Continuous wave radar is incapable of indicating the range of the target here. Only it can give the relative velocity of the target, but it is unable to find the range or the distance here. That is one of the limitation here, and this can be overcome in the next, that is the frequency modulated continuous wave radar here. That is the frequency modulated continuous wave Doppler radar. If continuous wave Doppler radar uses the frequency modulation, then the radar is called as the FMCW Doppler radar, or simply FMCW radar, that is frequency modulated continuous wave radar. Instead of transmitting the signal or radiating the signal as it is here, if you observe here, instead of the radiating the continuous signals as it is, those signals are frequency modulated here. At the transmitting end, those are frequency modulated, and afterwards those are radiated here. That type of the radar is called as the FMCW radar here. The main advantage is what? It measures not only the speed of the target, but also the distance of the target from the radar. That is, CW is incapable there. It is not able to find the distance, but here it is measuring the speed as well as the target distance here. Now, suppose we want to find the distance from the radar station. Suppose this is the radar station and this is the target. We want to find the range here. Then what is the equation here? The distance R, it is given by the delta T into C divided by 2. That is the delta T into C divided by 2. That is the distance from the station to the target here. This is the equation where R is the distance from the transmitter to target here. This distance is the R here. And delta T is the time taken by the pulse to travel from transmitter to target and back from target to receiver here. That is the two-way journey here. From the transmitter to target, again from target to again here receiver section here. That total time, what is the time taken, that is called as the delta T here. And C is the velocity of the light, and it is equal to the velocity of the electromagnetic waves here. That is the known value here. Therefore, if we know this particular delta T, the time here, then easily we can find out the distance here. That is delta T, that is the time difference, is given by the T2 minus T1 here. T1 is the time at which the signals are radiated here, and T2 is the time duration at which the signals are coming back to the receiver, or the echo signal is reaching the receiver section. Therefore, that T2 minus T1 gives the delta T. By using this one, we can find out the delta T. C is also known value. Therefore, R we can measure the distance here. Now, how to find out, how to mark here T2 and T1? That is, if instead of the continuous signal, if you are having the frequency modulated signal, then we can easily mark their frequencies here. At what frequency the signal is radiated from the radar station towards the target, and at what frequency the echo signal is coming back there. If the frequency variation is there, means easily we can mark the frequencies, the transmitted frequency, and the at what frequency the echo signal is coming back. And this time and frequency are directly linked here. Therefore, if we know this delta F, directly it is like we are knowing the delta T. Therefore, we can find out easily the particular distance here. Now consider the unmodulated continuous wave here. Suppose this is the unmodulated continuous wave. It is having the same frequency here. The frequency is same here. Therefore, if you are transmitting this signal, we are unable to mark here at what frequency the ray is transmitted and at what frequency the ray is received here. Therefore, unmodulated continuous means it is not capable here. But instead of this waveform, if you go for the modulated here, for example, this is the frequency modulated continuous wave. This is the modulating signal, sawtooth wave we are taken as the modulating signal here. According to this sawtooth wave, the frequency is varied here. For example, here the amplitude is increasing here. Therefore, from this lower frequency to the frequency is increasing here. Frequency is increasing and it is the highest at the maximum point. Again, the frequency will reduce there. Therefore, according to this information, the frequency is varying. Now, if we transmit this type of waveform, that is the frequency modulated waveform from the station towards the target, what will happen? Easily we can make out, okay, at this particular frequency, the ray is transmitted, and at this particular frequency, F2, the ray is echo signal is received. Now we are having the F1 and F2, and we can easily find out the delta F, and that is directly linked to the delta T. Therefore, if we know the delta T, easily we can find out the distance there. This is the basic principle which is used in the FMCW to find the range here. Now the block diagram of the FMCW, if you observe here, we are having the transmitting antenna and the receiving antenna. Both are the different sections we are using here. And this is the continuous wave transmitter oscillator. At the transmitter section, if you observe, sawtooth wave generator. This is acting as the modulating signal here. Now, this modulating signal is given to the frequency modulator here. It will vary the continuous waves frequencies here. Now, that is given to the oscillator, and that is through the antenna radiated here. Now, after striking the target here, the echo signal will be reaching the station once again. The receiving antenna will receive that, and that is given to the first stage, that is the mixer here. If you observe here, that part of the transmitted signal, it is also applied to the mixer, to the receiving mixer. Now here you will get the FD here, shift in the frequency, that is the Doppler shift. Along with that, the frequency variation here, F2 and F1 we are having here, and those are amplified here. Those are amplified, and we are having the limiter, that is the amplitude limiter here. The main purpose of the amplitude limiter is, if any variations are there in the amplitude, those should be removed. It should make the amplitude as a constant, because our information is available in the frequency variation, not in the amplitude variation. Therefore, amplitude limiter is used to make the constant amplitude, and afterwards it is given to the frequency counter here. The frequency counter, and it will calibrate it as the to measure the distance and the particular relative velocity here, because it is having the both the information FD and F1, F2. Therefore, that information is given to the indicator, and it will display in the form of the what is the relative velocity and what is the distance from the target here. Therefore, this FMCW radar is used to find the relative velocity as well as the distance here. Just we will analyze once again this particular block diagram here. We will get the clarification. Now here, as we have explained there, we are having the transmitter section and the receiver section. This is the frequency modulated continuous wave radar. Now, from at the transmitter section, what is happening? it is having the sawtooth wave generator. It is the modulating signal here. That is given to the frequency modulator such that here the signals are modulated here. Now that is given to the transmitter section, and through this the transmitting antenna to radiate the signal. Means here the sawtooth, the modulating signal is given to the modulator, and it continuous waves are modulated and those are radiated. And if you observe here, the part of the signal is also given to the receiver mixer here. Whatever they are transmitting, that is given to the receiver mixer also here. Now the receiver section here, the receiving antenna will receive the echo signal, and that is given to the receiver mixer here, and the part of the transmitted signal also applied here, such that output will get it as the only the shift here, FD, and the frequency variations here. Now that signal is amplified here, and that is given to the amplitude limiter to remove any variations in the amplitude, as you know, because we are having the information in the frequency change but not in the amplitude variation here. Now that is applied to the frequency counter such that to measure that frequencies and to calibrate, to indicate it as the in the form of the relative velocity and the distance here. Therefore that is given to the indicator here to display the relative velocity and the distance. This is the explanation for the FMCW. Now the advantages here. If you go for the advantages, there is no limit on the minimum range. Here there is no limit for the minimum range. Simple low power equipment can be used in case of the FMCW, and also the small antennas can be used to reduce the size of the equipment here. Next we will go to the next topic, that is the MTI radar. MTI radar means what? It is the moving target indicator here. Moving target indicator. The moving target indicator radar is a pulsed radar that uses the Doppler frequency shift as a means for discriminating the moving targets from the stationary object. Means moving target indicator is an pulsed radar. It is using the, again the principal Doppler frequency. That is, it is using the Doppler frequency shift to differentiate between the moving target and the stationary objects here. Now this is the block diagram here for the moving target. If you observe here, this is the duplexer because we are using the same antenna section here. We are using the same antenna section to transmit and receive. Therefore, to protect the receiver section from the transmitter section, we are using the duplexer here. Now we are at the transmitter section. If you observe, this is the transmitter mixer here. Transmitter mixer. At the transmitter mixer, we are having two signals. That is the stable local oscillator frequency, one oscillator here, and one more is the coherent oscillator here. One more is the coherent oscillator. The main purpose of the coherent oscillator is it will take care that the transmitted signal and the reference signal at the receiver, are in phase. And also the stable local oscillator, it will provides the translation in the frequencies at the transmitter and the receiver section here. Now this F0 and FC, this coherent frequency is usually it is same as the IF oscillator here. Whatever the coherent frequency is there, it is designed to match with the IF oscillator here. Now this stable local oscillator and F0 and this FC, both are mixed here, and that is given to the amplification. Usually the klystron amplifier is used and applied to the duplexer through the antenna section to radiate the signal here. Now once it is radiated and once it is reaching the target, the echo signal is coming back. Now that is collected here in the mixer one, and again this stable local oscillator signal is applied here along with the echo signal. This mixer will remove this stable local signal from the echo signal, which is having this stable local oscillator frequency here. Now here we are having only the IF, that is the FC coherent signal here, that is amplified and that is applied to the phase detector here. Now the input to the phase detector is, one is the received echo signal and one is the reference signal here. The output of the phase detector, it is the phase sensitive here. That is, it will generate the output voltage depending on the phase difference between these two inputs here. Depending on the phase difference between these two inputs here. Now, suppose see here, this is the phase detector. Now, for the stationary objects, always the phase will remain same there. At any time, if you measure means the phase difference between the transmitted and the received echo signal, it will remain same here. For example, for at the time t1, if you observe the time t1, the phase is, for example, that output generated will be x here for the stationary object. Now after some time also if you measure, then what will happen? Again at the time t2, for example, at the time t2 here, again the output will be here x only here at the phase detector, because for the stationary object the phase will remain same here. Now this is given to the amplifier 1. First at the t1, whatever the x is given, it is given to the amplifier 1, and after some delay, at the delay line is used such that to provide some delay here, and we are getting the t2 here. The output is given to the amplifier 2, and those two are given to the subtractor circuit here. Now what will happen? It will subtracts the this with this. Now for the stationary objects, both are same only, because always the phase difference will get same for the stationary objects. Now at the output will be getting 0, therefore there is no signal here. It is not detected here. But if you consider here, now if you consider the moving target here, for the moving target, what will happen? Again, this is the echo signal, and this is the reference signal from the transmitter section here. For the moving target, every time the phase difference between these two will changes. Continuously it is changing here. Now, for example, at the instant it is the output is x here, t1, and at the instant t2, for example, because for the moving target it will be continuously changing here. It is y here. It is y, means at here you'll get the x is applied here at the amplifier 1, and at t2 after some time delay we'll be having the t2 here. Therefore here the y is applied here. Now the x and y both are applied to the subtractor circuit. Now we'll be having the output as the z here. It is for the moving target here, not for the stationary. It is for the moving target. Therefore output will be detected at the display. That the output will be detected for the only moving targets here, not for the stationary. Therefore here it is called as the moving target indicator to identify the moving targets here. Now let us analyze the same block diagram once again using the mind map here. If you observe here, this is the transmitter section, this is the receiver section here, and this is the duplexer, because we are using the same antenna for the transmission and the receiving purpose here. Now the duplexer, it is connected to the antenna section to radiate the signal and to receive the signal here. At the transmitter end, here it is the transmitter section. Two signals are combined here. One is the stable local oscillator signal, and other is the coherent oscillator here, that is F0 and FC. Both are mixed in this mixer, and that is given to the power amplifier here. And the modulator is used because it is the pulsed amplifier, pulse type of the radar here, to switch the on and off, to switch the transmitter circuit on and off. The modulator is used here. Now this is the transmitting section. Now we can see this stable local oscillator. It is also connected to the receiver mixer here. Now when the signals are received here through the antenna, duplexer will give that signal to the receiving section here or the receiver mixer, and one more signal is stable local oscillator signal also mixing up to remove this F0, and here you will get only that FC, same as the IF signal here. Now that is given to the phase detector to compare with the reference, that is the coherent signal also given. This transmitted and the received signal phases are compared, and output is generated such that it is whatever the phase difference is there, depending on that the output signal is generated here at the phase detector. First time at the T1, it is given to the amplifier, and after some time, that is delay line is provided and at T2 the signal is taken and that is given to the amplifier 2 here. One is T1 and one is T2, and after that those signals are given to the subtractor here. This and this both are applied into the subtractor, because for the stationary objects you will get the same signal. After delay also you are having the same output here, and first at the T1 also you are having the same, because the phase is not changing there. There is the zero shift in the phase between those two here. Always it will be remaining constant here. Therefore output will get as the 0 here for the stationary. But for the moving targets, every time the phase difference between these two is changing here. That is from the transmitted and the received echo signal. Therefore you are having some output, and that is given to the indicator, and that will indicate the at what position the moving targets are present here. Now let us see here with waveform we can make out. Suppose here the if you observe here, this is the phase differences which are obtained from the stationary objects here, and these are the phases which are obtained from the outputs obtained from the moving targets here. Now here it is always remaining same here, output is remaining same, but here for the moving target it is continuously changing here. Therefore when those are subtracted at the output of the subtractor, these two will get cancelled, but for the moving target we are having some output there, the output is present there. Therefore this is detected as the particular moving target. For example, one is taken at the instant T1 one signal, and other is taken at the instant T2 here. Therefore those two are subtracted, and since here the phase is continuously changing here, we'll get the output as the some output will be available for the moving targets here. Okay, now about the blind speed here, that is the in the moving target indicator, one of the limitation is the blind speed here. That is, what is the blind speeds? In case of the moving target, as we have indicated, the continuously for the stationary targets, the phase difference between the transmitted and the received echo signal is same. Continuously it is same. It is not changing here. But for the case of the moving target, it is continuously changing. Therefore, the signals where we are getting the for example here we are getting the different in the phases, but here it is the constant here. Therefore constant means the phase difference between those two is remaining same, means it is nothing but the zero phase difference there. That is, it will be like there is no phase difference between the continuously it will be maintaining the same here, but here continuously it is changing. Now the blind speed means what? That is, suppose here it is the 0 degree here. Now here if it come to the 360 degree, this point is the 360 degree, means if the target is moving in such a way that it is generating the phase difference that is equal to 360 degree here. If that is equal to 360 degree, then what will happen? Thus, whatever the moving targets are there, they will appear as the stationary, because it is nothing but like 0 here. It is not providing any variations in the phase, same phase. 360 is nothing but it is like the 0 here. Therefore, it is not providing any variations in the phase. Therefore, that will appear as the stationary object here. That will appear as the stationary object. Now, that is one of the major limitations of the moving target indicator, and that particular speed with which the target is moving, that is called as the blind speed here. Means where the phase difference it is providing 360 degree, then that is called as the blind speed here. And with blind speeds, moving target will appear as the stationary target here. It is unable to detect whether it is moving or stationary. It will mark it as the stationary only. Now, what is the blind speed here equation? It is lambda divided by 2 TS, where V blind is the one of the blind speeds here, and lambda is the wavelength of the transmitted pulse, and the TS is the pulse repetition time. Now, how to overcome with this blind speed problem here? That is that the solution for the blind speed problem is to have the variable PRF. If we are having the variable PRF, then we can overcome with this blind speed here. Okay. Now let us have some MCQ quiz here. Okay, students, answer honestly and participate. The first question is the Coho in MTI radar operates at the intermediate frequency, transmitted frequency, received frequency, pulse repetition time. Let's try to answer this. Which is the correct option? Yes, it is the option A here. That is, the Coho MTI radar operates at the intermediate frequency. The function of the Chord's delay line in MTI radar is to help in subtracting a complete scan from the previous scan, match the phase of the Coho and the stable local oscillator, match the phase of the Coho and the output oscillator, none of the above here. And what is the purpose of the delay line here in the MTI? Let's try to answer. Yes, the correct answer is it is option A, because it will help in the subtracting the complete scan from the previous scan here. That is, we are taking one at T1 and one at T2 here. A solution to the blind speed problem is to change the Doppler frequency, to vary the PRF, to use the monopulse, to use MTI. And the solution is, yes, the solution for the blind speed is how we can eliminate this problem. Try to recall that. Yes, correct answer is the option P here. Next question is the blind speed problem appears in which type of radar here? That is pulse radar, continuous wave radar, FMCW radar, or it is in MTI radar. Where we are facing this problem? Yes, in continuous wave radar? No, the correct option is option D, that is MTI radar in the moving target indicator. Blind speed causes targets to appear moving uniformly, fluctuating, stationary, or intermittently. Yes, what is the solution here? Whether they will give the output as a fluctuating or moving. The correct option is option C, that is stationary. In the blind speed, even though target is moving, but they will appear as a stationary here. A FMCW radar can measure only relative velocity, only range, relative velocity and range, relative velocity and size of the target here. Yes, what it will measure? Whether it is only relative velocity or it is only range. What is the correct option? Yes, right. The correct option is option C, because it is giving both velocity and the range here. The STLO stands for standard local oscillator, stable linear oscillator, stable local oscillator, or it is saturated and linear oscillator. What is the correct option? Yes, it is option C, that is stable local oscillator. Echoes from fixed target vary in amplitude. vary in frequency, vary in pulse interval, remains constant. Which is the correct option for the fixed target if the target is stationary? Yes, the correct option is option D, remains constant, because for the fixed target we are not having any change in the phase here. They will be detected as the stationary here. Okay, one and all. Thank you for watching.